Gallus. We're going to talk about some fascinating work on causal assumptions in Bell experiments.
Thank you very much. And thanks to the organizers for this very nice and pleasant conference. It's a great idea also to do it in Westport. I've never been here, but I have to say I enjoyed it much and have missed the Irish rain, so it's all perfect. This is joint work with Paweł Blasiak, who spent the last year in the US in California in Chapman. He's now back in Poland, for those who know him. And it's actually work extending quite very, I guess, philosophical almost foundational questions around what can you do in order to generate a certain given statistics. So, for you who heard yesterday's talk of Julian Beck's very excellent talk about process matrices, this is not about process matrices. So this is actually, in a way, a simpler question, and it's essentially around, well, if we have statistics like those which are generated by Bell experiments, and that's a given, and we take the view that we do want some sort of causal explanation for it, which either comes from a very sophisticated mathematical model putting together relativity and quantum mechanics, or from something else, then what can we actually do to explain that? We know from Bell's work that essentially the most common sense assumption that basically you can have allies involved on various sides, they receive entangled particles, it's all local, they can all decide freely on the measurement directions of the detectors, nothing weird happens. If you put all that together, then you get Bell inequality, and we know that's violated in nature. So the question we're asking is, well, if you still want a causal explanation, what do you need to do? And we're looking at three things, so there's the locality, free choice, and for this conference especially, the error of time. So if you can play with any of those elements, that's a part of your causal graph, then does it tell you anything? Can you have violations in one way, which gets the statistics, or other violations maybe not sufficient to generate this? So this is kind of the background. Three relatively diverse philosophical concepts: locality, free choice of detector settings, and I mean in experience mostly realized by pure random number generators, but in theory also realizable by human decision making, and the error of time, which is a certain implicit assumption of that things should only go forward. So putting those together, what does this get us? And
sorry, to break the flow, just we haven't shared the screen.
sure. Great, thank you. Thank you very much. No problem. So this is the outline. After a short introduction, I want to basically run through various causal graphs that could be used to describe a Bell experiment. Actually, there's no time there in the sense that we don't actually have to know when detectors click. We just have to be able to identify pairs of entangled particles. That's kind of the only thing for time. And then there will be effectively the question of, well, what does it mean to have a purely local model? What does it mean to have a free choice model where detectors can be set freely? And specifically, well, is there another way of explaining the Bell observations or the violations of Bell inequalities that you observe if we assume that the error of time is, at least as far as hidden parameters are concerned, not strictly kept? And so after going through all these, I will say something around causal explainability of experimental statistics and how the various graphs effectively can do this. And then I will present a measure that Paweł Blasiak has developed, which is the causal fraction, which is basically the question of, well, if you have a certain causal model to generate the Bell statistic, and you know you have to kind of cheat somewhere sometimes. So in some experimental runs you have to break locality, in some you may have to break the error of time. How often do you have to do that? So in order to generate the statistics, it's an interesting question of, well, what's the minimal resource consumption of these violations? And that's what the causal fraction is about. It's basically the cost of violating any of these given assumptions and basically counting, not the time, but the number of instances of entangled particles when that needs to happen. After that, I'll do the conclusion. And I want to note for some reason. Okay, great. Thank you very much. So Bell inequality is confirmed by experiments shown in the classical worldview, as they put together very obvious assumptions which we all hold dear in our daily lives. Nevertheless, when you put them together into the language of a causal graph, especially into like causal Bayesian models, which the language I'll be using are the DAGs, the directed acyclical graphs, like Julia Kroll and our team have pioneered it, then effectively it allows you to use these philosophical terms and make them into a mathematical model with local arrows. And this is the way we will express Bell's theorem, and we will then discover the assumptions which are an arrow at time, and we choice for the participants, Alice and Bob, to set their measurements. Now, if we accept this as a fundamental concept and say, well, this is something which has to be observed in nature, either because it's emergent from some sort of equations, or because we actually believe it's a driving principle, then what the Bell inequalities and the Bell experiments tells us that at least one of those assumptions, locality, arrow of time, and free choice, one of those must fail. Not in all experimental settings, but in some of them. And then if you have a maximum number of violations in the classical Bell setup, you get the Tillerson bound, and you know, well, you have to have fails of those assumptions, not in 100% of the trials, but in a certain percentage, and like 40 something percent, which is a thing you can derive. So this gives you a number on the number of fails you have. And our goal here was to find a quantitative comparison of violations, these causal assumptions, and the measure of merit we've chosen is the frequency of such violations. So what does this mean in numbers? Well, the usual Bell setup, which you're all familiar with, you have some sort of source creating a pair of entangled particles, one particle going to Alice and one going to Bob. And now we all, at least I don't know really what's behind the entanglement, so it's something weird, something hidden in a way, at least for me, so this is the lambda, which is effectively a hidden parameter of the model. The other things you can observe. So you can observe basically what the outcome is that Alice's measures, that's the A. You can observe the outcome for Bob measures, which is the B. And you can also observe the measurement settings that Alice has chosen, which is the X, and the one that Bob has chosen. Now, the paradox from the Bell experiment only arises once you bring the data together. If you just have Alice sitting on one side, doing something in her lab, Bob being on another planet, doing something in his lab, there's no paradox then. It's only actually, again, when you can bring this data together, which, again, is then limited by the speed that you can have the information. But this is not the Bell experiment. And in this experiment, effectively, you can model it with a DAG. This is this graph we have here, a directed acyclical graph, which basically gives all the parameters we have, the X and the A, from the Alice side, and the Y and the B from the Bob side. And then this lambda, which is sort of our hidden variable element, which gives us the entanglement. Now, arrows in these diagrams, they show causal relationships, and also quite importantly, the arrows that are not here, because the arrows that are not here show a lack of a direct causal relation. Of course, you can still have if you have a very complicated model with lots of arrows, you can have indirect relationships, but this one's pretty simple. So this basically tells us in the standard assumption, there is no arrow from X to B, for example, simply because whatever Alice decides to measure does not influence the outcome that Bob will find, which is B. At least that's the normal assumption we'll have. This would be consistent with the locality approach. Also, you have arrows here in case of lambda, so the entanglement somehow has an impact on what Alice sees and has an impact on what Bob sees. And again, you have an arrow from the measurement that Bob chooses and the outcome that Bob also chooses. But that's all you have. And now, if you take it as given, then effectively, first, this DAG allows you the derivation of the Bell inequalities. And we know from various experiments, from the Nobel Prize last year, that those are effectively violated. So something cannot work like this. The question obviously is which one? And the way we approach is that we say, well, let's say there's an experimental statistics, which is this P. So P is a statistic depending on 5 things, A, B, X, Y, and lambda. And we just don't know where it comes from, it's there. P especially does not need any time, because P is generated by all the records that Bob and Alice have during the experiments, and it's put together with somebody when Alice and Bob meet and exchange their data. Now the job we're looking at is, well, can we generate this by a set of 3 parameters? And this is on the other side, these are the ones that's tilde. So the P tilde is stuff, let's say I have the job of trying to find a way of generating the statistics, I can choose the P tildes. And in this model, the only thing I can choose are these 5 things. And for example, p tilde a given x lambda means I can choose something for the distribution of a on the basis of x and lambda. But you notice, for example, there's no b here and there's no y here, and this is the restriction of the model. So I don't have full freedom. It's not a fully complete graph, but I have some freedom. Now, from the derivation of the Bell inequalities, we know this thing means, for example, the CSHA's inequalities, that this have to be cannot exceed 2. We know from the Bell experiments they can go up to 2.82 something, so we know there's a violation. Now, the question is, well, how can we come up with that violation? And if you think about it, the only way is basically you give extra arrows, and these are the ones in red. So here, it's the standard explanation that people say, oh, the wall is non-local. That this is typically what they tend to mean, which somehow means Alice's choice of her measurement setting x influences Bob's outcome b instantaneously. Some people call it violation of locality. Some people call it parameter dependence because basically x and b is dependent on x. In our picture, it's just this red arrow. And the interesting thing is, in a physical basis, in a time-space arrangement, it actually is a weird thing because Alice does not necessarily have to know where Bob sits. And even the entangled part of the particle that Alice has does not sort of know in any way where Bob may have chosen his detector to do his experiment. It doesn't even know actually when Bob does that. So it's not that the timestamps have to agree between Alice and Bob. It's just we have to have a way of saying, well, this photon that Alice has measured is entangled with the other photon that Bob measured, so we have to have these sort of matching, but it doesn't mean they have to have them at the same time. There can be other matching principles. But doing this arrow basically means, well, there's some instantaneous influence here, and this somehow probably has to have a physical mechanism. Of course, this challenges Einstein's theory of relativity, as it suggests some sort of non-local mechanism, and that's typically why people say, oh, well, we know the word is non-local, but that's not the only way to see it. And mathematically, it just means that P, which we want to generate, is a product now again of this 5 P tildes, but you see this little red X here, hope you see it, but this little red X makes a difference, which basically means that now your distribution of P can also depend upon X is 2. So I have a little bit more freedom in choosing my parameters. And this would be a DAG with a violation of locality. Now, it's not the only way you can do it. It's a nice thing once you have a DAG, you can say, well, how many arrows can I put there? Of course, you can put like 3, 4 arrows, but that's not what we wanted to do. So we say, let's say 1 arrow has to be enough. So now the other question is, well, where you can put the arrow. And you can, of course, put it like this. You can say, well, X actually somehow acts to the creation of the entanglement into the lambda. That's pretty weird, definitely. And so this would basically mean Alice's choice of setting X affects the hidden variable lambda in the past. Because it's a hidden variable, it's not meaning automatically you created a time machine, but it still is something weird. And it's not our idea, it's 2 interesting papers from Adam, for example, 2 roads to retrocausality, and another very good one from Wharton and Agraman, the colloquial summary, Bell's theorem, locally mediated reformulations, quantum mechanics, which are but it does challenge the conventional understanding of the flow of time. And mathematically, it now gives you the ability to put an X in this distribution, your free parameter P tilde lambda, because your lambda now stands on X. Next way to do it is to say, well, maybe I have the other way around. So lambda somehow influences X, which is commonly interpreted as saying restrict the free choice that Alice had. That's even weirder in my view, because it kind of means that Alice is not completely free when she decides what direction to measure on her entangled particle. Some people call this measurement dependence, which sort of is pretty innocent, but if you think about it, it's actually pretty close to superdeterminism, or superdeterminism is one example of how you can create this. I don't know actually of many good other examples which do not somehow go into superdeterminism. But this basically means that Alice is not completely free in making her choice. Mathematically, it gives you the parameter here that the P tilde, your X, is now conditional on lambda. Again, 1 more degree of freedom. So we have these 3 things. And well, you can say, okay, what else? Do you have any other errors? Turns out, actually, not really. These are the only 3 kind of reasonable possibilities. Let's look at the top row here. So you see an arrow from Y to A. Yeah, you can do that, but okay, what does it mean? If you flip Alice and Bob, which is the names for Alice and Bob, the only thing you do is to get what we already defined as non-locality. So this is equivalent to saying an arrow from X to B. So not X to B. You can of course have the arrow from Y to lambda, which again is a one-way of read from causality. And you could have an arrow from lambda to Y, again, which is the same in terms of no free choice, because now you would restrict the free choice a bit more. Top row, yeah, kind of these geometrical cases can be treated by switching the rows to two rows. Nothing fundamental. The other things, well, that's the bottom row here. And those are also even weirder. They sometimes so weird that they don't have a name, but at least we can find one. So this one, when you have an arrow from X to Y, you can say, well, I'm sure we call it XY, non-locality. Weird term, but I haven't read it anywhere. But basically, it's a weird concept anyway, because this thing would be a mixture of more than one assumption. You would break locality, and you would also break the free choice of Bob, somehow depending on what Alice has. So it's kind of a really strange concept, which we can discard. The other reasonable thing is, and this had a name, this is outcome dependence, when you say, well, what about arrow from A to B? Is this enough? And it turns out, well, it's enough if you only have two choices of measurement. But if you have 3, 4 more choices of measurements, and obviously Alice has a lot of freedom in saying how she wants to have her orientation of the measurement device, then it's not enough anymore. So once you have actually more than 2 outcomes, then effectively, when Alice has a choice of 3 settings, then this outcome dependence is not sufficient to simulate the observed statistics. This has also been proven. That's actually work by Chavez in 2015, the defined framework for realization of the causal assumption theorem. So actually, yeah, you can do that, but it's not enough to explain what you see. And the last one, which again is not really used in the literature, we call it outcome neutral causality. It's actually putting an arrow from A down to lambda. Again, weird, it's some form of neutral causality, but it's not enough. And first, if you do that, you have to kill the arrow, which normally goes from lambda to A, because simply our DHGs are acyclical. If I would have both arrows, I get like a weird causal loop, which these DHGs don't allow. So if I want that, I actually have to kill that arrow, and then I get an arrow from A to lambda. And then when you basically get a chain, so X influences A influences lambda, lambda influences B. But that chain is not enough. It's like the outcome dependence here. And basically, it's a way of rephrasing it into the outcome of the causality to outcome dependence. So it's not enough to create statistics we see. Which basically means, okay, we are left with the 3 things I presented earlier. The DHG for non-locality, the DHG for non-free choice, and the DHG for free choice. So far so good. So what's the goal? Well, we don't use any process matrix, any nothing. We actually take a very simple picture. We just say, let's say we found the experiment, we brought the data together, and we have a series. I call it a time series, but actually it's a bit of a stupid term because we don't need the time really. We just need to identify which particle that Alice measures is entangled with other particle that Bob measures. Time is usually used in experiments to create that timestamp and that relation, but basically it's pretty relational. So once you've figured out which is entangled with what, you can do the statistics. The statistics is basically a series, a sequence of quadruplets, A, B, X, Y, and this generates the statistics, which you can now compute by simply counting. So PXY is your probability distribution of measurement settings, and PAB, given XY, is the probability of the outcomes given the measurement settings. Now we know the baseline GAG, so the one without the red arrows, is not enough to explain the observed statistics. What we can now prove is that any of the 3 other DAGs, the one with 1 red arrow, any of them is enough to create the statistics that we see in the other experiments. So first, before we do that, well, we have to say these 3 DAGs with 1 red arrow, they're not fully general. So if you remember them, they don't have arrows everywhere. DAG which has arrows everywhere means everything depends on everything, which doesn't get you very far. But these things are not. These things just one red arrow. And if you analyze them, you'll find, well, they have some one thing in common. So all these 3 DAGs basically all imply a condition, which we call the dependence condition. And it basically means, in this DAG language, that A is independent on Y, conditional on X. So that's the first independence, basically because the outcome proposed by Alice does not depend on the choice of Bob's measurement, given we know what Alice is doing. And the other one is that x is independent of y, which again means that there is no influence between the choice that Alice takes to the choice that Bob makes in this measurements. So these are the things, and these are all basically a consequence, a mathematical consequence of the DAGs. So it's one thing, it's pretty easy, you see it from the picture. The other thing is slightly more complicated, which means if you have the independence condition, then mathematically that's already enough to prove that your DAG, for example, the Locality DAG, is enough to create statistics. And I'll just give you a quick proof of this one, just to see a flavor of how these things are. They're actually, these type of mathematics is not very sort of, there's nothing really complicated in them, it's more like probability theory. So we would basically create the probability distribution A given x, which is basically a sum of the probability distribution over all outcomes that we may observe. That's well defined. If we know the general statistics, we can define the marginals, pxy, which is basically the product of the choices of Gallus and Bob, which is basically some of these things. We have to have two sets, with one set x for the set of possible measurement settings that Alice can choose. We assume that we define it, otherwise you get a lot of measure theory and it's not really adding anything. And we also have to have another set, which is A, which is the finite set of possible outcomes. Now, the trick is the following. The distribution PA given x, this can be composed as to sort of deterministic strategies. And the only thing you have to consider really is, well, how many functions do I get mathematically from the set x to the set A? Both sets are finite, then it's a finite number of functions, and you just go through the various functions that exist. So basically, this Kronecker A equals f1x, and any probability that a certain function is used, then this is enough to effectively give you the probability distribution of A given x. That's all the depths of the created of 3 that you have. And PF is anything, any well-normalized distribution, which basically sums up to that. Now, you can show, using the setup, that any of your three graphs with one red arrow is enough to create the distribution you want. So this consequence on time, so in the sense what I'm looking at is the special case that I'm looking at the DAG, which allows me to do causality. So what I'll do is now I basically say, okay, my hidden variable space, it's just the product of the set of all possible functions with the product of the set of all possible measurements, which means any hidden variable is just a combination, lambda is just a function f, and a certain measurement setting x tilde. And once you have that, you can effectively define your three parameters. Remember, all the ones with the tilde are the ones that are free. We can effectively put what we want. If we put it like this, your p tilde a given x lambda being the Kronecker function of the function f of x taking the value a, and so on, then this is exactly the right mathematical setup to give you what you want. To define these 5 things. And having defined those 5 things, you now have to compute that the resulting statistic is the one that the Bell experiment generates. That's happening here. So basically, I'm summing up over all possible values of the given parameter lambda, and this is basically how my tilde functions generate the final distribution. So this is the sum over all possible values of lambda, and now I just put in the various terms I defined before. So this first one is, for example, the Kronecker function. The second one here is this conditional probability, and the last one here is the Kronecker function of x being x tilde and the function f being what it is. So now you can basically put this in. Now basically your x tilde only has the value of these two things coincide, which basically means wherever your x tilde you can write an x. And now you have this simplification. Then you basically say, okay, this only lives when a takes the value f of x. So this f of x can be replaced by an a, which simplifies this further. And now you still have the sum over all possible functions. And the possible functions are, well, we're taking the value a, which means this whole sum collapses. So this pf actually becomes effectively what we need for this one value. And then you have this thing, and now pax cancels out, and you're left with pabxy. Well, what's the point? Well, this is the distribution we wanted, whereas the p tildes are the distributions we put in. And this basically shows that we can generate the distribution that we wanted. There's not even necessarily quantum mechanics involved in here, because this works for anything which is put into the causal relationship. And the other relationship here is pretty trivial, because this is the way. So what does it mean? Well, it means if we have a retrocausal assumption, or equivalently, if we take a non-locality assumption, then we get the statistics we want. And now the question comes, well, what's the most efficient way of doing this? So the presence of an additional red error may not be needed in all instances. Again, we say times here, but times here have to be careful because it's just about the number of experimental runs when you identify entangled particles. So the fractional causal approach basically says, well, what's the smallest number of these red errors? When can I come up with a strategy where I don't need it very often? And that basically means you look at a convex combination of any experimental statistics that satisfies the independence condition, and then you write it like this. The P star is basically any sort of statistics you can get from the baseline DAG, so the one without a red error. And the other one is the sort of statistics you can get from, let's say, a retrocausal model. And then you have a convex combination between those two with a parameter Q. And now the question is, what's kind of the minimum Q I can use? So of course, if you want to say, well, my view of the world is still that it should be mostly local, mostly free choice, mostly low causality, then you would like to have a Q which is very low. And so the way we define the causal fraction basically is saying, well, we can go for the minimum Q, which gives us the composition, but of course we can't restrict the freedom here, so basically we want to do it for all distributions of measurement settings, X and Y. So this is basically the causal fraction, for example, for radio causality. It's the smallest Q you need under all possible distributions of PXY to generate the bell statistics that was observed. So in words, basically, the causal fraction assesses how many times the red error needs to be in effect to reproduce the observed behavior for any distribution of settings. And then mathematically, you can prove a theorem which goes like this. For all distributions and all statistical behaviors satisfying the independence condition, then these three causal measures do agree. So basically, your measure of non-locality is the same as your measure of microcausality is the same as the measure of non-free choice. And that's now a mathematical fact. Also, you come with very different philosophical interpretations of those. Once you've framed them into a DAG, you can prove some statements. In this case, all three measures will be maybe not enough time to prove. But basically, this is what we have. So, study of Bell inequalities and causal assumptions, we think, provides some insight into the fundamental nature of reality, the possible rules, especially for extending our physical theory. Violations of these causal assumptions have important implications for our worldview and possible developments in new theories. So what we've shown is that the concept of these causal fractions agree, and they offer a quantitative measure to effectively compare the strength of the causal error. So not just saying, oh, we have a causal relationship, but going a bit beyond that and saying, oh, we have a causal relationship, but we don't need it in all instances to get the desired statistics. And now we have the equivalence. You can actually also compute these causal measures. And we can jump to that. I don't have enough time for that. But basically, you can show additional theorems, which means that it's not just you can say these three measures agree. You can actually put them, for example, to the CSH quantity. So this, for example, says if I have any sort of non-signaling behavior, the three measures agree, we've shown. But also, they can be computed from the CSH expressions. You need the 4 CSH expressions in a setting where you only have binary choice of measurement. And then basically these compute very neatly from the biggest of 4 S quantities. So for example, if you take a PR box, which you know S can go up to 4, then this means that you have 1/2 times 4 minus 1 gives you basically 1, which means 100% of the experimental trials you need to violate one of the given assumptions. If you don't have a PR box, then you come up to the Thirlton's bound, for example, and you get to 2.2, and then you're in around like 41%. There's one thing you can compute. This is very generic. You can do this on the quantum mechanics, but actually you really need quantum mechanics for this. Here you actually need to effectively just say two choices of measurement. You can go the other direction as well. You can say, well, maybe I actually have infinite number of measurements because Alice can be very granular of how she orients her measurement to get to the vectors. And then you can actually relate to all the results. For example, this one from EPR2 and Portman from Kiajuzin, which basically says if you have a maximum entangled state, 2-qubit state, then effectively you can also compute the fractions basically using these older results where people already computed the non-local fraction as the 1 minus theta of the cosine. Thank you very much.
Questions? Just come up to the microphone, please, if you could. Yeah, I don't mind. You go first.
Thanks for the very nice talk. My question is related to the non-locality that you presented is in a Bell experiment where the violation comes from entanglement. But could that be also applied to the situations where the violations come from non-commutativity of measurements? That sometimes non-locality comes not from entangled particles or entanglement, but from non-commutativity.
I think yes, because the only thing we really use is the DAG. So in the DAG language, we make a distinction between this one, the baseline, and the one where we add an arrow. So it doesn't really matter what's the source of that. It's just the question is, can you put what you're up to into DAG language of that form, and then you can use it.
Thank you. One more question. Back there.
Yeah, thank you very much as well. What do you think of the hypothesis of lambda being not in space-time, being a non-spatiotemporal cause, which means that it wouldn't be drawn like this? It's not my idea. I think it was in later Bell's work also.
You mean that lambda is not part of classical space-time?
Yeah, and so it would be a physical object that is not spatiotemporal.
Yeah, I think that's an interesting hypothesis. And the thing about these DAGs is they don't need the classical space-time to make it. It's about relations between the various things you can measure.
They actually need it because lambda is before x and y, so it means it's in time.
Well, yes and no. Yeah, I mean, in the sense that in the classical presentation you're right, that people would say, okay, I have the entanglement, which is lambda, and then sort of I spread my particles. But I mean, what you could do here, if lambda is just something which sits outside space-time, you can still have a relational thing like it's drawn with the arrows. I mean, the arrows themselves in the GG model don't presuppose that you have a temporal structure and then you're even inside time.
But I thought that the direction of the arrows indicates.
Yes, that's why I give it the number retrocausality. If you basically say lambda is outside space and time, then the term retrocausality wouldn't make any sense. You would have to call it something, I don't know, something pointing to outside of space and time, whatever that is.
Okay.
Thank you.
Thank you very much. So let's move on. Let's take a speaker.